The water cycle, also known as the hydrological cycle or the H2O cycle, describes the continuous movement of water on, above and below the surface of the Earth. The mass of water on Earth remains fairly constant over time, but the partitioning of the water into the major reservoirs, vice, fresh water, saline water and atmospheric water, is variable depending on a wide range of climatic variables. The water moves from one reservoir to another, such as from river to ocean, or from the ocean to the atmosphere, by the physical processes of evaporation, condensation, precipitation, infiltration, runoff, and subsurface flow. In doing so, the water goes through different phases: liquid, solid, and gas. The water cycle involves the exchange of energy, which leads to temperature changes. For instance, when water evaporates, it takes up energy from its surroundings and cools the environment. When it condenses, it releases energy and warms the environment. These heat exchanges influence climate. The evaporative phase of the cycle purifies water, which then replenishes the land with fresh water. The flow of liquid water and ice transports minerals across the globe. It is also involved in reshaping the geological features of the Earth, through processes including erosion and sedimentation. The water cycle is also essential for the maintenance of most life and ecosystems on the planet. Description: the sun, which drives the water cycle, heats water in oceans and seas. Water evaporates as water vapor into the air. Ice, rain and snow can sublimate directly into water vapor. Evapotranspiration is water transpired from plants and evaporated from the soil. Water vapor molecule H2O has less density compared to the major components of the atmosphere, nitrogen and oxygen, N2 and O2. Due to the significant difference in molecular mass, water vapor in gas form gain height in open air as a result of buoyancy. However, as altitude increases, air pressure decreases and the temperature drops. The lowered temperature causes water vapor to condense into a tiny liquid water droplet which is heavier than the air, such that it falls unless supported by an updraft. A huge concentration of these droplets over a large space up in the atmosphere become visible as cloud. Fog is formed if the water vapor condense near ground level, as a result of moist air and cool air collision or an abrupt reduction in air pressure. Air currents move water vapor around the globe. Cloud particles collide, grow, and fall out of the upper atmospheric layers as precipitation. Some precipitation falls as snow, hail, sleet, and can accumulate as ice caps and glaciers, which can store frozen water for thousands of years. Most water falls back into the oceans or onto land as rain, where the water flows over the ground as surface runoff. A portion of runoff enters rivers in valleys in the landscape, with stream flow moving water towards the oceans. Runoff and water emerging from the ground may be stored as freshwater in lakes. Not all runoff flows into rivers, much of it soaks into the ground as infiltration. Some water infiltrates deep into the ground and replenishes aquifers, which can store fresh water for long periods of time. Some infiltration stays close to the land surface and can seep back into surface water bodies as groundwater discharge. Some groundwater finds openings in the land surface and comes out as freshwater springs. In river valleys and floodplains there is often continuous water exchange between surface water and groundwater in the hyporheic zone. Over time, the water returns to the ocean to continue the water cycle. Process is precipitation, condensed water vapor that falls to the Earth's surface. Most precipitation occurs as rain, but also includes snow, hail, fog, drip, graupel, and sleet. Approximately 505,000 cubic kilometers of water falls as precipitation each year, 398,000 cubic kilometers of it over the oceans. The rain on land contains 160 7,000 cubic kilometers of water per year and a snowing only 1,000 cubic kilometers. 78% of global precipitation occurs over the ocean. Canopy interception. The precipitation that is intercepted by plant foliage eventually evaporates back to the atmosphere rather than falling to the ground. Snow melt. The runoff produced by melting snow. Runoff, the variety of ways by which water moves across the land. This includes both surface runoff and channel runoff. As it flows, the water may seep into the ground, evaporate into the air, become stored in lakes or reservoirs, or be extracted for agricultural or other human uses. Infiltration, the flow of water from the ground's surface into the ground. Once infiltrated, the water becomes soil moisture or groundwater. A recent global study using water-stable isotopes, however, shows that not all soil moisture is equally available for groundwater recharge or for plant transpiration. Subsurface flow, the flow of water underground, in the vadose zone and aquifers. Subsurface water may return to the surface, or eventually seep into the oceans. Water returns to the land surface at lower elevation than where it infiltrated, under the force of gravity or gravity-induced pressures. Groundwater tends to move slowly, and is replenished slowly, so it can remain in aquifers for thousands of years. Evaporation, the transformation of water from liquid to gas phases as it moves from the ground or bodies of water into the overlying atmosphere. The source of energy for evaporation is primarily solar radiation. Evaporation often implicitly includes transpiration from plants, though together they are specifically referred to as evapotranspiration. Total annual evapotranspiration amounts to approximately 505,000 cubic kilometers of water, 434,000 cubic kilometers of which evaporates from the oceans. 86% of global evaporation occurs over the ocean. Sublimation, the state change directly from solid water to water vapor. Deposition, this refers to changing of water vapor directly to ice. Advection, the movement of water in solid, liquid, or vapor states through the atmosphere. Without advection, water that evaporated over the oceans could not precipitate over land. Condensation, the transformation of water vapor to liquid water droplets in the air, creating clouds and fog. Transpiration, the release of water vapor from plants and soil into the air. Water vapor is a gas that cannot be seen. Percolation, water flows vertically through the soil and rocks under the influence of gravity plate tectonics. Water enters the mantle via subduction of oceanic crust. Water returns to the surface via volcanism. Water cycle thus involves many of the intermediate processes. Residence times. The residence time of a reservoir within the hydrologic cycle is the average time a water molecule will spend in that reservoir. It is a measure of the average age of the water in that reservoir. Groundwater can spend over 10,000 years beneath Earth's surface before leaving. Particularly old groundwater is called fossil water. Water stored in the soil remains there very briefly, because it is spread thinly across the Earth, and is readily lost by evaporation, transpiration, stream flow, or groundwater recharge. After evaporating, the residence time in the atmosphere is about 9 days before condensing and falling to the Earth as precipitation. The major ice sheets, Antarctica and Greenland, store ice for very long periods. Ice from Antarctica has been reliably dated to 800,000 years before present, though the average residence time is shorter. In hydrology, residence times can be estimated in two ways. The more common method relies on the principle of conservation of mass and assumes the amount of water in a given reservoir is roughly constant. With this method, residence times are estimated by dividing the volume of the reservoir by the rate by which water either enters or exits the reservoir. Conceptually, this is equivalent to timing how long it would take the reservoir to become filled from empty if no water were to leave. An alternative method to estimate residence times, which is gaining in popularity for dating groundwater, is the use of isotopic techniques. This is done in the subfield of isotope hydrology. Changes over time. The water cycle describes the processes that drive the movement of water throughout the hydrosphere. However, much more water is in storage for long periods of time than is actually moving through the cycle. The storehouses for the vast majority of all water on Earth are the oceans. It is estimated that of the 332,500,000 cubic miles of the world's water supply, about 321 million cubic miles is stored in oceans, or about 97%. It is also estimated that the oceans supply about 90% of the evaporated water that goes into the water cycle. During colder climatic periods, more ice caps and glaciers form, and enough of the global water supply accumulates as ice to lessen the amounts in other parts of the water cycle. The reverse is true during warm periods. During the last ice age, glaciers covered almost one-third of Earth's land mass, with the result being that the oceans were about 400 feet lower than today. During the last global warm spell, about 125,000 years ago, the seas were about 18 feet higher than they are now. About 3 million years ago, the oceans could have been up to 165 feet higher. The scientific consensus expressed in the 2007 Intergovernmental Panel on Climate Change summary for policymakers is for the water cycle to continue to intensify throughout the 21st century, though this does not mean that precipitation will increase in all regions. In subtropical land areas, places that are already relatively dry, precipitation is projected to decrease during the 21st century, increasing the probability of drought. The drying is projected to be strongest near the poleward margins of the subtropics. Annual precipitation amounts are expected to increase in near-equatorial regions that tend to be wet in the present climate, and also at high latitudes. These large-scale patterns are present in nearly all of the climate model simulations conducted at several international research centers as part of the fourth assessment of the IPCC. There is now ample evidence that increased hydrologic variability and change in climate has and will continue to have a profound impact on the water sector through the hydrologic cycle. Water availability, water demand, and water allocation at the global, regional, basin, and local levels. Research published in 2012 in Science based on surface ocean salinity over the period 1950 to 2000 confirmed this projection of an intensified global water cycle, with salty areas becoming more saline and fresher areas becoming more fresh over the period. Fundamental thermodynamics and climate models suggest that dry regions will become drier and wet regions will become wetter in response to warming. Efforts to detect this long-term response in sparse surface observations of rainfall and evaporation remain ambiguous. We show that ocean salinity patterns express an identifiable fingerprint of an intensifying water cycle. Our 50-year observed global surface salinity changes, combined with changes from global climate models, present robust evidence of an intensified global water cycle at a rate of 8 plus or minus 5% per degree of surface warming. This rate is double the response projected by current generation climate models and suggests that a substantial intensification of the global water cycle will occur in a future 2 degrees to 3 degrees warmer world. An instrument carried by the SAGD satellite launched in June 2011 measures global sea surface salinity, but data collection began only in June 2011. Glacial retreat is also an example of a changing water cycle, where the supply of water to glaciers from precipitation cannot keep up with the loss of water from melting and sublimation. Glacial retreat since 1850 has been extensive. Human activities that alter the water cycle include agriculture, industry, alteration of the chemical composition of the atmosphere, construction of dams, deforestation and afforestation, removal of groundwater from wells, water abstraction from rivers, urbanization, effects on climate. The water cycle is powered from solar energy. 86% of the global evaporation occurs from the oceans, reducing the temperature by evaporative cooling. Without the cooling, the effect of evaporation on the greenhouse effect would lead to a much higher surface temperature of 67 degrees Celsius, and a warmer planet. Aquifer drawdown or overdrafting and the pumping of fossil water increases the total amount of water in the hydrosphere, and has been postulated to be a contributor to sea level rise. Effects on biogeochemical cycling. While the water cycle is itself a biogeochemical cycle, flow of water over and beneath the Earth is a key component of the cycling of other biogeochemicals. Runoff is responsible for almost all of the transport of eroded sediment and phosphorus from land to water bodies. The salinity of the oceans is derived from erosion and transport of dissolved salts from the land. Cultural eutrophication of lakes is primarily due to phosphorus applied in excess to agricultural fields in fertilizers, and then transported overland and down rivers. Both runoff and groundwater flow play significant roles in transporting nitrogen from the land to water bodies. The dead zone at the outlet of the Mississippi River is a consequence of nitrates from fertilizer being carried off agricultural fields and funneled down the river system to the Gulf of Mexico. Runoff also plays a part in the carbon cycle, again through the transport of eroded rock and soil. Slow loss over geologic time. The hydrodynamic wind within the upper portion of a planet's atmosphere allows light chemical elements such as hydrogen to move up to the exobase, the lower limit of the exosphere, where the gases can then reach escape velocity, entering outer space without impacting other particles of gas. This type of gas loss from a planet into space is known as planetary wind. Planets with hot lower atmospheres could result in humid upper atmospheres that accelerate the loss of hydrogen. History of hydrologic cycle theory. Floating landmass. In ancient times, it was thought that the landmass floated on a body of water, and that most of the water in rivers has its origin under the earth. Examples of this belief can be found in the works of Homer. Source of rain. In the ancient Near East, Hebrew scholars observed that even though the rivers ran into the sea never became full. Some scholars conclude that the water cycle was described completely during this time in this passage. The wind goeth toward the south, and turneth about into the north, it whirleth about continually, and the wind returneth again according to its circuits. All the rivers run into the sea, yet the sea is not full, and to the place from whence the rivers come, thither they return again. Scholars are not in agreement as to the date of Ecclesiastes, though most scholars point to a date during the time of Solomon, the son of David and Bathsheba, 3,000 years ago. There is some agreement that the time period is 962–922 BCE. Furthermore, it was also observed that when the clouds were full, they emptied rain on the earth. In addition, during 793–740 BCE, a Hebrew prophet, Amos, stated that water comes from the sea and is poured out on the earth. Precipitation and percolation. In the Aditya-hridayam of Ramayana, a Hindu epic dated to the 4th century BC, it is mentioned in the 22nd verse that the sun heats up water and sends it down as rain. By roughly 500 BCE, Greek scholars were speculating that much of the water in rivers can be attributed to rain. The origin of rain was also known by then. These scholars maintained the belief, however, that water rising up through the earth contributed a great deal to rivers. Examples of this thinking included Anaximander and Xenophanes of Colophon. Chinese scholars such as Cai Nisu and Lu Shi-Tun-Qiu had similar thoughts. The idea that the water cycle is a closed cycle can be found in the works of Anaxagoras of Clazomenae and Diogenes of Apollonia. Both Plato and Aristotle speculated about percolation as part of the water cycle. Precipitation alone. In the biblical book of Job, dated between 7th and 2nd centuries BCE, there is a description of precipitation in the hydrologic cycle. For he maketh smaller drops of water, they pour down rain according to the vapor thereof, which the clouds do drop and distill upon man abundantly. Also found in the book of Ecclesiastes, all the rivers flow into the sea, yet the sea is not full. To the place where the rivers flow, that they flow again. Quote, up to the time of the Renaissance, it was thought that precipitation alone was insufficient to feed rivers for a complete water cycle, and that underground water pushing upwards from the oceans were the main contributors to river water. Bartholomew of England held this view, as did Leonardo da Vinci and Athanasius Kircher, the first published thinker to assert that rainfall alone was sufficient for the maintenance of rivers was Bernard Palissy, who is often credited as the discoverer of the modern theory of the water cycle. Palissy's theories were not tested scientifically until 1674 in a study commonly attributed to Pierre Perrot. Even then, these beliefs were not accepted in mainstream science until the early 19th century.